Once more into the breach, dear friends. First speaker this morning, François Gay-Balmaz. So let's flex with François.
Thank you very much. So first of all, let me thank the organizers for giving me the opportunity to give this talk. So it's a joint work with my colleague Vakhtang PUTKARADZE from University of Alberta, and it's about the geometry of a very specific problem of fluid structure interaction, which concern flexible tubes conveying fluid. So before I start, let me a little bit explain the context of my research. So as you will see, it's very geometric. So our research is mainly about developing geometric tools to study continuum mechanics, fluid mechanics, or nonlinear elasticity. And with this tool, we can do many things. So basically, we can do modeling, right? Derive new models that include new physical effects using geometric approach. We can also derive associated numerical schemes that preserve the geometry of the problem. Recently, we can also include the irreversible process, still by keeping the geometric structure well understood. So by geometric structure, what I mean are these things here. So what we want to understand in a physical system is first the configuration manifold, the Lie group symmetries, variational principles, all these kind of structures. So today I will mainly stick to variational principles and symmetries, but other structures may also appear. And some of these structures are well known, right? You know them. It's Lagrangian, Hamiltonian reduction, symmetry, variational principles. It's very useful to include constraints, right? Could they be holonomic or not? These approaches are very good to include them. And as I said, now we also know how to handle irreversible process. So this is a little bit what I said, right? Three main directions that in which we can hope to make some progress. So one of them is very interesting also for a numerical side, because once we really understand the variational principles, the conservation laws, the symmetries of the systems, there is a whole discrete analog of that can be used to derive numerical schemes that for some aspects are better than others. So today I will mainly illustrate A and B, right? So geometric modeling and numerics. The example I take is the fluid conveying tube, but we are also doing some other example with these methods. So, as I said, today is about variational principles, so I cannot avoid recalling the old classical Hamilton's principle, right? Once you have a physical system, you know the configuration space. You have your Lagrangian that depends on the position and velocity. The equation of motion should be, in fact, obtained by Hamilton's principle. Of course, this is trivial in classical mechanics in a finite dimensional space. But I will use this in an infinite dimensional context. I mean, for fluids, elasticities, things like that. So this is less usual, I would say. Then, usually, these Q dot are not the variable that you really work with. You have in your hands other variables. And often these other variables emerge from these initial ones because you have some symmetry in the problem. For example, your Lagrangian is invariant under the action of a Lie group. So you can reduce this space. Yeah, you reduce by the Lie group symmetry. You get some reduced Lagrangian. And now you simplify the system because it's smaller dimension, but the price you have to pay is that the variational principle is more complicated, right? It's no more the classical Hamilton's principle is more difficult. You take only specific variations of your curve. So these two lines here are really at the core of what I will do today, right? But these reduction, I mean by symmetry, are not some mathematical constructions only. They have physical meaning. For fluid dynamics, for example, this corresponds to passing from the Lagrangian to the Eulerian description. This is associated to relabeling symmetry. But in other contexts, like in multi-body dynamics or in the elastic part of the problem that I will describe today, the reduction is not to Eulerian, it's to body frame representation. So it's a left invariance, right? If you have invariance under relabeling symmetries, you go from Lagrangian to spatial description. That's what you do in fluid dynamics. If you have left invariance, covariance of the space, right, the associate reduction by symmetry is the Lagrange to body frame description. So both of them will appear today because I will study the interaction between fluid and Couserat rod theory. So that's the setting. So once we have this in mind, I can now give the plan. I'm not sure I will do all, but I will start with flexible tubes conveying incompressible fluid, do some geometric modeling, how to derive the equations, because I will insert some new physical effects that were not present in earlier models. Some comment on instability and comparison with earlier works. Some discrete analog of that, variational discretization that respect the geometry of the problem. And finally, go to compressible gas and expandable walls. So in this case, the system admits shock waves. Okay, so this is the system we are studying, right? This is the physical system, but that's the mathematical one. So there are several ways to modelize this, depend on what effect you really want to include or not. So our setting will be to use a Couserat rod description of the tube. So the elastic part is using the Couserat theory, and the fluid is simply one-dimensional here. And what we include with respect to earlier works is the change of the effect of the change of the cross-sectional area. So when the tube bends, right, the cross-section, of course, decrease, and this has some effects on the dynamics. So if now I refer to my previous slide on variational principle, how can I derive the equation for the full dynamics, right? It's completely free, right? Both the tube and the fluid have their own dynamics. So I will first understand separately the problems and then couple them using the holonomic constraint. So it really fits with the previous talk, the previous slides that I was describing the context. So of course this is a very interesting problem. There has been a lot of work. I cannot even cite all the communities, but at the beginning at least there was two parallel progress, right, in the English and Russian literature. I really didn't know about that, but my colleague is Russian, so he knows also this side, and it's interesting to see the interplay of the two evolutions in parallel. Both of them were very successful in some sense. There have been several progress now, for example, how to modelize the fluid leaving the tube at the end. So this has been, for example, approached by the follower force method. This has these also good and less good points. There has been also progress using shell models. And the first really consistent fully, because some of these models are 2D and they are linear, but the first fully consistent theory in 3D has been developed here in this paper. And this is really an extension of the Kirchhoff rod equation to include fluid dynamics inside the rod. So that's a little bit a very quick overview of all what has been done. So what we will include is the change of the cross-section, its effect of the fluid structure interaction dynamics. The variational approach also gives necessarily, automatically, the the interacting forces that appears at the end of the tube, something that is very hard to compute in general, but with the variational formulation is automatic. And we will see at the end how we can also incorporate fluid dynamics. So this is the system, the geometry of the tube. Then I will revise the geometry of the fluid. So I adopt a Courserac model. So what do we need to describe such a system? We need first a curve like that, the centroid, right? The line of centroid. This is the curve R of Ts that describes this curve here. And at each point, you have an orthonormal frame. This is this lambda in SO3, it's a rotation matrix. So this is the configuration variables, R and lambda. So they form the configuration manifold, and it's already a good news. This configuration manifold is a Lie group, because I want to see these two maps with value in R3 times SO3, and for symmetry reason, it's good to see them in SE3. So we already understood some of the geometry, right? Then the dynamics, of course, depends on time derivative of these guys, spatial derivatives, but that's not the variables that are convenient to be used when you describe this kind of systems. What you really would like to use are the convective variables. So these are the same velocities and deformation gradient, but seen from a body frame. So seen from an observer that is attached to the frame here. So it simply amounts to multiply on the left by the rotation inverse, right? And you get 4 variables. So keep in mind these 4 variables because they will appear everywhere. So I have small letters for the angular and linear velocity, like in rigid body, nothing here special, omega, gamma. And I have large letters for the corresponding deformation gradient. So when I derive with respect to space. Okay, so these are the variables. So the link with reduction with symmetry was established in this paper. So now we need the Lagrangian. So I will take some usual expression, right? I have here the linear and angular kinetic energy of the tube dynamics, and here I have the simplest possible elastic potential here. So this involves deformation of the centroid, right? So shear and stretch, and here deformation of the cross section. Recall omega is this guy here. It's an angular gradient, right? And it's bending and twist. So I observe that this Lagrangian LQQ dot can be written in terms of these body variables. So this is already some indication that there is some symmetry. So to derive the equation of motion, in principle, I could just use Hamilton's principle and get the equation. But these are not the variables that are useful for the problem. The variables that are useful are these ones. So how to accommodate Hamilton's principle when I'm not using the traditional, the configuration variables. I'm using some transformed versions. So the first step is to understand that this rewriting is associated to a symmetry. I will not go into the details, but you have here the mathematical approach. And once you do this symmetry, you have to compute very specific variations of your variables, not the usual ones. So that's the result. I don't explain the theory, but the result is that one. Using Hamilton's principle with respect to ordinary variables, the configuration variables, Q dot, is the same as using some transformed variational principle for the convective variables. So remember, omega gamma and omega gamma are the convective variables, and they are the variation of them that you use in the principle are not arbitrary like in here. they have some constraints. So in fluid dynamics, you have seen these constraints. These are the lean constraints. But here, in this context, it's you have heard maybe it's Euler Poincaré reduction, but here I just do it explicitly, and they have this form. So what is free here is not the green term, but this sigma and psi. But anyway, when you compute here the variation, integrate by part, you isolate the free variations, you get something, and you get the equations. I don't write them because now I want to include the fluid dynamics. Then at the end I will show you what happens. So as I said, we want to include the motion of fluid inside to modelize the tube conveying fluid conveying tube, and we will proceed with several steps to achieve this goal. First, we understand that's not easy, as you will see, how to describe a moving fluid in a moving tube properly in geometric terms, how to include the constraint, the effect of the boundary force, and finally to derive the equations. So we assume no friction. We can include friction, but for simplicity we assume no friction in this talk, and we approximate the fluid by just 1D motion. We can do more, but just for here, for simplicity, it's already quite involved. So that's the model that we have to understand. Right? You have a moving tube given by RST. That's the position of the center line. But inside you have a moving fluid. So you cannot easily describe a moving fluid in a moving object. So one approach is to attribute to each fluid particle a label. This is standard, but not in this context. And to create a new set of labels, large S, right? And little s is the parameter of the tube. And to describe the motion with a map here, a diffeomorphism from the two S. And then you put this moving thing inside the tube using the tube variable, right? So once we understand that, we understand what's the configuration space of our system. So it's the space of tube motion that we have seen, SE3 valued maps, times this map here, the fluid configuration. But they go from somewhere, we don't know where, because it's a moving interval, because some particle will go out of the tube, some other enter, so it's an open system. So that's not easy from the point of view of configuration space, but we have this approach. And in principle, now we have the variables, and it only remains to see what the Lagrangian is and what the constraint is. Then we can derive the equations. So the constraint, I will wait a little bit before the constraint. What I need, in addition to this configuration map, I need also the mass density of the fluid. So the mass density of the fluid is transported by the fluid motion using this kind of transformation, right? It's a one-dimensional density, so it transforms like that. And once we have this, we are ready to include the constraint. So let me see how this works. So that's the density of the fluid times ds, so it's a volume. It's an infinitesimal volume occupied by the fluid at a certain configuration. But the fluid has to be in the tube that is itself moving, right? It has to be inside. So it has to fill this. So this is the constraint. This guy has to be equal to the area of the tube at the configuration omega gamma. You remember these are the tube variables. Here I'm really describing the fluid structure interaction, because I'm saying that the fluid volume agrees with the available volume in the tube. And this volume depends on the geometry of the tube dynamics. So that's a crucial equality. I'm really writing what I'm saying here. So now if I look a little bit more with a geometric approach, I see that this is a holonomic constraint because it does not depend on velocities. So we know how to include holonomic constraint in Hamilton's principle. It's trivial. We simply add a Lagrange multiplier. This wouldn't work with non-holonomic, but here it's holonomic. It's an infinite dimensional space with holonomic constraint, but still formally it works the same. And there are additional forces that are due to the fluid leaving the tube. So we also know how to include this in Hamilton's principle in general. So constraint, virtual work of the force. So that's very classical. We use this classical approach to a non-classical situation, I would say. So we notice several symmetries. You have the relabeling symmetry of the fluid, right? As I said, you have the left invariance of the tube, and with all these, the variables you really have to work with are not the configuration variable q dot in classical sense. These are the convective or body frame coordinates for the tube and spatial velocity for the fluid. So as before, we understand this process as a reduction by symmetry. I will not go into the details, but that's what it really is. So we can easily rewrite this guy in terms of this new variable. So that's what we do here. I don't explain all the details, but it's really systematically done using Hamilton's principle. So we have our Lagrangian, the constraint, right? Fluid volume, tube volume, and the virtual work of the force, only arising at the free end of the tube. We proceed with variations, compute, integrate by part, etc. You have certainly seen this kind of variation of fluid velocity, right? It's called the lean constraint. And we get some system. So for here, just don't be afraid of this partial derivative. This just means the partial derivative of the Lagrangian with respect to the corresponding variable. To get the equation, just take the Lagrangian you prefer and compute the partial derivative. But it's more elegant to keep this form because we really see the interaction of the term. So in green here you have the 1D fluid motion in the tube. It's now red. Then here you have the Kossera, in black you have the Kossera rod equation, and in green here you see the effect of the fluid acting on as a torque and as a linear force on the fluid on the tube variables. Mu, remember, is the Lagrange multiplier. No surprise, it can be identified with the pressure, more or less. And here in this term you have the variation of the area with respect to the tube variable. So that's really where the fluid structure interaction here is. You have some formula for the area. The way it depends on omega is multiplied by the pressure of the fluid, and this is the guy that really acts on the tube equations.
Is the area constrained to be circular? No.
Not here, but for our concrete calculations, yes. But no, this works for any kind of area. And so in addition to, so this is angular linear momentum, fluid momentum. In addition, we have mass fluid volume conservation, continuity equation for the mass density of the fluid. And what in addition gives the principle is it gives directly the expression of the force at the boundary exerted by the fluid leaving the tube. So that's something that is hard in general to compute. But here the variational principle directly gives me what are these forces. So if you choose some boundary condition for your free end of the tube, for example, vanishing stress, zero traction on the boundaries, you insert them in this expression. Here they are abstract, but you can just replace, and you get the force acted on the free extremity of the tube. So we did some stability analysis and comparison with earlier work. I will not go into the details, but if we linearize our system around the stride configuration, we get a Timoshenko-like model, right? But with fluid motion inside. So this is well known to be a linearized version of Kosterad-Rod theories. It's more precise than the Euler-Bernoulli beam equation. So, of course, consistently when we linearize this, we get Timoshenko beam with fluid inside. And for example, improvement of Euler-Bernoulli beam with fluid inside has been done. This is the green term here, due to pi do C and co-authors. And we see here that it's hard if you just have the linear theory. It's very hard to guess what could be the terms. Look at them, right? If you have in your hand only the Euler-Bernoulli beam equation, and you have to think how to insert a fluid moving inside. I mean, without using the general theory, it can be very hard, right? Because the variables mixed, and you get this fourth order equation. But in our approach, it's just you linearize and you get the system. So I will not go too much into the details, about the stability analysis of this, but morally speaking, allowing change of cross-section area in fact creates new instabilities for some wavelengths. So we have a whole study of this, but I will not go into the details. So then I will here be very brief, because I want to also approach the compressible motion. So just here some word about variational discretization. So once we have understood all this geometry, there are now some well-known approach to discretize these geometry. So these are called variational integrators. So if they are implemented only in discrete time, you get symplectic integrators, because they preserve the symplectic form, the Hamiltonian structure of the equation. So the idea is to discretize in time the Hamilton's principle. That's what I'm writing here. I don't explain the details, just I'm writing. This is a discrete version in time of what I did, but with an appropriate discrete Lagrangian. But you can also do this in space and time, which is the case of our problem, right? You take a discrete space-time Lagrangian, the one I showed before, discrete, and you take variations in the same way as I presented in the continuous case, but in discrete, and you get some discrete equations, of course. And it happens that these are very good numerical schemes for these complex problems, because they preserve the symmetries of the system, so they preserve the conservation laws. They also preserve the intrinsic geometry of the system. So this I will skip. So we did this for our problem, but I prefer to now focus on compressible gas. I think it's more interesting for us. So there are some complications now, some additional variables, because we assume that now the fluid motion inside is compressible. And consistently with this, we also assume that the tube can expand. So we add three variables: the entropy and mass density of the fluid. Right? It's a compressible gas, so it needs this with usual thermodynamic identities. And we also include the radius of the tube as a free variable, so it can expand due to the effect of fluid motion. So we keep all the geometry that I've described so far, but you will see the constraint is different. So for sure we will have two conservation law. We have the entropy equation, right, because we don't have any irreversible process yet. And here we have mass conservation for psi. Psi is not rho. This is the main difference here. There are two mass density. The mass per unit volume, rho, the one that is used in the internal energy, and the mass per unit length, the one that is preserved by the 1D motion, right? 1D motion preserves mass per unit length, not volume. So these are the two conservation laws that I have. But now they are related. The mass conservation by unit length, the density by unit length, and the density by unit volume are related using the area available to the fluid. Of course, this is trivial, but for us, this is a key point, because we will insert now this in the variational principle. So that's what we do, right? So in this color, you have the elastic variables. You have just r dot in addition, and the blue ones are the fluid variables. So you have ordinary Lagrangian, kinetic minus potential, and internal energy, and this internal energy depends on the mass density by unit volume, and this is the one by unit length divided by the area available to the tube. So it's very natural, but when you use this in the variational principle, it gives really new equations, and they are really easy. You just compute, integrate by part. So this is the key writing, right? Observe that the internal energy of the fluid depends on the mechanical variable of the tube. So this complicates the theory. Yeah? Okay, so I'm almost at the end. What I want to say is that instead of having a constraint, I have this, and I can derive the same kind of equations using Hamilton's principle. Again, no details, ordinary variables to current variables is using geometric process of reduction, and you have to use constraint variation. So what we observed nicely is that we were able to derive the Rankine-Hugoniot condition for the shock waves inside the tube, and how the elastic variables impact on the motion of the shock, right? So here we assume a shock in mass density and in fluid momentum and in energy. And we get a jump in entropy too that has to satisfy the second law. So this is an example of a shock wave that propagates in a tube, where here we assume no rotational motion, just to simplify. So we checked really that our model admits such shock wave solutions in 1D. Okay, so I'll let you read the conclusions, but it's basically summarizing what I did. So the big lesson is to identify the correct geometry and apply a classical variational principle that you modify according to your problem. If you have a holonomic constraint or a symmetry, etc., you can always do this. And I didn't show, but we extend well-known models. So our model is not completely different. It's just some consistent generalization of earlier model of collapsible tube. Okay, I will finish here.
Thank you. Questions? Every now and then I go to a conference and somebody mentions Kosarat elasticity, and I go back and I try and understand what it is. And I very much would like not to go to the grave without an understanding of what the hell it is. Can you recommend any book or reference that explains the basis and the necessity of this theory?
a book, I would
Or anything that makes sense to the.
Something that really makes sense is this Marsden paper. If you like geometry, I must say. If you like geometry, this is the most understandable paper.
Good.
But what is Coursera theory? It's elasticity in 1, 2, or 3D, and to each particle you attach a degree of freedom, SO3. That's what it is.
Thank you.
In my case, it's simple.
I will do my homework. Thank you.
François, you didn't show any results, so can you tell us what you've learned about any particular system using your approach?
So I skipped a little bit. So we study the instability, right, and we compare with experiment. So we have a colleague here. I didn't show the movies.
This is the heart of the matter.
I concentrate on the geometry because so where is this? So we have a colleague who actually did experiment of our model here, and we compare. So this is he uses medical tube, right? In which case the change of cross section makes a big impact on the instability, right? So we were able to confront our result. So our result is here for specific values of the parameters here. So here you have the K is the impact, the scale of the cross section, how much the cross section change impact in the dynamics. Where is it? Too many here. So we choose this volume formula, right, for the tube, for the cross section. So it's undeformed one, but modified by the omega variables, right? So this K here, the large it is, the impact of the cross-sectional deformation is. And you see here, we computed the velocity, the critical velocity, according to the value of K. So as if K increase, of course, this critical velocity. And we compare with traditional models that do not take into account of this change of cross-section. And but we see that for some value it coincides, but for others that are confirmed in our experiment, I will show you the movie privately. I should have shown them. It's different. And there is no reason to expect that when K is 0, we agree with. This is Paiducis model, right? There is no reason. Because even in this case, our model is different. It's not Euler beam, it's Timochenko beam. So that's one part of our.
I'm just wondering.
We have also other results here, but okay, we can discuss.
If I may add on what Gray was suggesting is, well, you considered a variation of cross sections, right, in the simulation.
Yeah.
But if you, of course, I appreciate the generality of your approach, but if you consider bending, high bending, then you even are far away from the cross section being circular, because you have to take into account ellipticity.
Absolutely.
And that is very important.
That's very important.
Both from a
We
fluid
know that.
viewpoint and structural viewpoint.
Yeah. So we know that, and we are working on that, in fact, very seriously.
So it's
Because R, this is too simple. R, right? It's just radial deformation. It's not good. We need long and small axes and repeat this. So technically speaking, we can do it, but you know, it's a long way from this to having the.
Okay, I'm afraid we're going to have to set aside the questions. So.